Good afternoon. Welcome to today's webinar, Passenger Ejection from Golf Carts and Low-Speed Vehicles. Due to several environmental, social, and economic factors, the use of golf carts with limited speeds of 12 to 15 miles an hour and low-speed vehicles with limited speed of 25 miles per hour has become increasingly prevalent in recent years. These vehicles are no longer exclusively found on golf courses, but in residential areas, universities, and business complexes. With the increase in the number of these vehicles utilized by the general public, the injury rate due to golf cart accidents has increased. It is estimated that there are approximately 48,255 golf cart-related accidents during the years 2002 to 2005. One of the leading causes of golf cart injuries is ejection from the vehicle. It is estimated that 45% of golf cart injuries occur due to a person falling off the vehicle when it is moving. Rear-facing passengers are often the victims of golf cart ejection due to their orientation in the vehicle. During this program, the presenter will cover typical products, typical accidents, current restraints available on golf carts and low-speed vehicles, the accelerations of passenger experiences during sharp maneuvers, measurement examples, accident reconstructions, and restraints modifications. The presenter for today's program is Dr. Oren Masory. Oren holds a Bachelor of Science, Master's of Science, and PhD in Mechanical Engineering from the Technion, Israel Institute of Technology. Currently, he's a professor in the Department of Ocean and Mechanical Engineering at Florida Atlantic University. He has over 30 years of mechanical engineering experience. He has served as a litigation and engineering consultant and held positions in industry. His research interests include robotics, automation, machine tools controls, assistive technology, and accident reconstruction. Dr. Masory is an expert on vehicular accident reconstruction, low-speed rear-end collision, slips, trips, and falls, pedestrian accidents, machinery, product liability, building and safety codes, speed and distance analysis. Oren has written numerous reports and articles for major publications on the above topics. He holds membership in ASTM and SAE. During today's program, we will take questions throughout the program. If you have a question, please use the chat or Q&A feature located on the right-hand side of the screen to submit your question. We will answer the questions in the order in which they come. Tomorrow morning, I'll send out an email with a link to the archived recording of the program, and I do ask that you take time to fill out the survey that will appear on your screen after today's program is over. I'm now excited to turn the presentation over to our distinguished guest, Dr. Oren Masory. Oren, the program is now all yours.
Thank you very much. First of all, good afternoon to everybody. I know it's 2 o'clock. In Florida, it's very warm and hot, and everybody wants to take a nap. But we'll go through this seminar, in reasonable space and time. So what I'm going to talk about is golf cart ejection. My student Kyle Shaw could not make it, so I have to present this myself. Somehow I don't see the arrow to advance.
Oren, if you take your cursor and if you put it over that blue and green globe that appears to the left of your name.
Oh.
And then go north, you should, and to the left, you should see a text box that says 01 golf ejection. Oren, are you there?
Oh, here, I see it. Okay.
There you go. You got it.
Okay, I'm sorry about this. Okay, first of all, what kind of vehicles we are talking about? Everybody's familiar with the golf cart. And then there are three which are not very well known. One is called LSV, which is low-speed vehicle, with the top speed of 20 to 25 miles per hour. And then there are similar vehicles like personal neighborhood vehicle, neighborhood electric vehicle, etc., which are being used in relatively large communities, also in some large facilities. Here at Florida Atlantic University, we probably have hundreds or more of these kinds of vehicles. The difference between them is that the regular golf cart is limited to a maximum speed of 20 miles per hour, while the LSV can reach up to 25. Now, these carts come in different shapes and different kind of visuals, but obviously all of them are the same, and which comply with this limitation that I've talked about. Some people in some neighborhoods really love them very, very much. And you can see some of them have like a Rolls Royce here up here, some Jeeps, and who knows what. There are probably 50 or 100 different kind of styles. From accident point of view, there were about 150,000 accidents in the period of 1990 to 2006. Ejection counts to 45% of the injuries, and more than 25% are involved with head and neck injuries, and you'll see this later on from the biomechanics point of view. Once you fall from the car, there's a good chance that you are going to hit your head. The location of these accidents most of the time is in recreational facilities. In particular, when it comes to golf courses in some hilly surfaces, because they are not stable, and once you go down the hill and maybe make some kind of a turn, they have the tendency to tip over. 15% of the accidents were on city streets, which are obviously very severe, and the others are at home, farms, and some other facilities. What's the regulation and standards? They're very, very little. SAE defines some safety issues for low-speed vehicles. NC talks about also safety requirements, and 49 CFR talks about low-speed vehicles. All of them are talking about these particular features: headlamps, stop lamps, turn signals, etc., etc. When it comes to LSV, it is the only vehicle where it has to have a seat belt. Unfortunately, the fact that you have a seat belt, nobody enforced the use of these seat belts, and this obviously is a major concern. Here in Florida, you can see some of this LSV with seat belts, but I never ever saw somebody really using it. Now, what kind of restraints we have? Most of the time we have this hip restraints, which comes in different sizes and different shapes. I'm sure you can follow my mouse here. Here is one very, very typical. This is a different one. Some of them don't have any. For example, this one, the green one. Some of them are very, very, very small. And it just depends on the manufacturer. and there is no particular regulation. Here are some of the aftermarket products like the seat belts, and you can see also that this is the hip restraints which came from the manufacturer. I'm looking at this particular person. It seems to me he's very responsible, the fact that he installed them. What kind of accidents? Tip-over accidents are all over the place, and you can see this over and over. These are some examples. Some of the examples here are looks like on a golf cart, some on streets. This is like a street. Some of them because of high maneuver and very slippery conditions. And this is the one that I really like, the one on the bottom left, which is tip over in a golf course. And I can tell you what, and that's what happened. Obviously, nobody wants to take any responsibility for that. The other kind of accidents are the street accidents, and these are some examples. And you can imagine that the golf cart or the LSV are not designed as a street vehicle, and therefore they are very, very dangerous because they don't have the stiffness or any impact protection from a regular vehicle which was designed for some kind of collision. So if you look at the bottom here, I can imagine what happened to the driver here. If you look at the top figure here, again, you have a direct intrusion into the passenger seat. The government does very little, maybe one or two tests of impact of this vehicle, so there's no statistical information. Some of the accidents are self-imposed, and people lose control going to the woods, as you see here, or in many cases, they go to the water and see what happened here. This, it will play again, but these two guys, you see these two guys are standing on the back of the vehicle, and if each of them is like 200 pounds, they just apply 400 pounds and the whole vehicle tipped over. And these two, this lady and this man, came out, you know, really lucky. I don't know this person what exactly he wants to do, but it doesn't look very, very safe to me. And this particular father is you know, irresponsible. Anything that will happen to this vehicle, this little baby will fly. We have plenty of accidents where these vehicles are in an environment where there's a lot of water, like in Florida. We have canals and ponds and lakes, and many of them next to golf courses, and you find them in the water many, many times. Now, what's the problem? The problem is the following. First of all, the number of golf carts or the same increasing all the time. It becomes to be very, very popular, and some cities also allow you to use this in the city streets. So people feel, okay, I'm going to take my golf cart and drive to the store rather than to use my my vehicle. Second or third, there is no need for a license. There is no any authority which says you cannot drive this. And as a result of this, kids at the age of 13, 14 are using this in the neighborhood and without any licensing. And once they are out of sight of their parents, you never know what they are going to do. They might go and show off to their friends, and this will cause accidents and some other troubles. And the last issue is there's no enforcement of the use of seatbelt, even though in some vehicles seatbelts is required. Okay, ejection, as I said before, is the major issue in this accident, and that's what I want to talk about and spend most of the time. And this happens in the following cases. First, when you have very high-speed turning, there is lateral acceleration which will try to push you out of the vehicle. If you have very high acceleration, the people are sitting at the back will experience a force which will push them out of the vehicle. If you have very high deceleration, which is like a hard stop, the people in the front will move forward because of this. And obviously, combination of these three accelerations will result a larger acceleration in a certain direction, and that's I'll show this in a minute. For high-speed turning, this is the right turn, this is the left turn, this is the radius of turning, this is your velocity, this is the acceleration that you experience, and it's function of the speed square divided by the radius of curvature here. Now, don't forget, the roads that we have are basically not circle, but each time you are making a left turn, right turn, or any kind of there's any curvature in the road, this equation is correct once you know what is the radius of curvature at that point. Now, this is just to give you an idea of what kind of accelerations we are talking about. So what you see on this axis is the radius of the curvature, and what you see here is the traveling speed. So let's take one example here. If you drive at, let's say, 12 miles per hour, which is not very, very fast, and you make a turn at about 15 feet radius, you are going to experience acceleration of 0.65 g. Now, what does it mean? It means that at the center of gravity of the body of this person, somebody applies a force which is 65% of his weight. So for myself, if I weigh like 150 pounds and I'm at 0.65 g, there is a force of 150 multiplied by 0.65, which will push me or pull me in a particular direction. This is a very large force. It's not something that we can ignore. The same data I just plotted slightly different, and it shows that I can reach very high accelerations. Let's say this is like 0.6 for different radiuses at different velocities. For example, if I'm at this point, I can drive at 16 miles per hour, and the radius is 30 feet. And I can do the same if I'm driving like, let's say, 14, and the radius is 25 feet. So there's a whole set of conditions which I can reach very high accelerations either by changing the speed or by changing the radius of turning. Okay, so let's take one at a time. Our measurements show that if you hit the pedal, it doesn't matter if it's electrical or a gas engine. We did our experiments on electrical vehicle, and the maximum acceleration is about 0.3 g, which means that there is a force which is 30% of the weight of the person that push him backward. Okay, think about you sitting in the car and you push the gas pedal. Eventually, you can feel as you accelerate that your back is being pushed against the seat, the support of the seat. When you are stopping, this is a very hard stop. I assume coefficient of friction on the road is about 0.65. So you are going to experience about 0.65 G force forward. This is the same as you are hitting your brakes very, very hard, and therefore your body is moving forward. And what really holds you is either the seat belt or, in the worst case, the airbag deployed. So now what I'm going to show is configurations of this different accelerations, and I made like a green circle for low risk, a yellow for moderate and high, and red for high risk. And here's an example. Let's assume I'm just doing forward acceleration. Forward acceleration, it means that the driver and the front passenger are moving backward, and therefore the back support provides support and nothing happens. On the other hand, the two passengers sitting in the back facing back, there is acceleration in this direction, and since there is no seat belt to tie them to the seat or any particular restraint that will prevent them to move in this direction, they might fall. But since the acceleration is relatively low, we said like 0.3 G, I made this in yellow and says, okay, this is some kind of a moderate risk. If I'm looking for forward deceleration, this is where I'm hitting the brakes. The driver eventually experiences very high acceleration forward, but since he's holding the steering wheel, he has something to support himself. The back passengers, they experience the same kind of thing, but they are being supported by the back support of the seat, and therefore nothing happened to them. On the other hand, if you look at the front passenger, he experienced very high acceleration forward. If there is no seat belt, the best he can do is eventually move forward and support himself with his hands at the front dash of the vehicle, and that's why I assigned this like a yellow risk or a moderate risk. Talking about right and left turn. When you turn right, which is in this direction, the acceleration is to the left. In all cases, as you see in a second, the driver is always safe. And, and the reason he won't be ejected because he's holding the steering wheel. I'm not talking about the case where the car tips. I'm talking about the cases when a person is being ejected. The front passenger experiences the same force to the left, but the worst case is going to hit the driver, which will provide him for some support. The back passengers, the one on the left-hand side is in risk because the only restraint that prevent him to eject is the hip restraint, which is right here, and it depends how high the hip restraint. If it's too low, he might tip over it. And this passenger, he is a little bit less because either he will be supported by this passenger, or if this passenger is not, he might just fall on the seat. In a similar way, when we turn to the left, Eventually, this is the same story. But at this time, the passenger, the front passenger, has the same risk as the rear passenger because the only thing between him and being ejected is the hip restraint here and the hip restraint here.
Oren, just very briefly, we had a question come in about these diagrams from Kimberly. She wants to know, is the diagram assuming a complete back seat or the passenger standing in the back of the golf cart?
I assume that the people are sitting in the back seat of the golf cart. The forces are independent if they are sitting or standing. This is just description of the what kind of forces acting with. Once we know the accelerations and the forces, then we can apply this to the person, either if sitting or if he's standing. And I'll show you simulations, very shortly.
Just one other question, Oren, about these diagrams. This comes from Christopher, who asks, how does the force that you talked about affect, how is the force affected if the golf cart is lifted higher than a stock golf cart, such as one at a golf course? In other words, a cart that's customized to be lifted with bigger tires.
Well, the force will be the same force. What will happen with the vehicle itself, if the vehicle is very, very, very high, obviously it tends to tip by far easier. My concern at this point is not the tip over of the vehicle. I'm concerned about forces acting on the passenger, which might cause the ejection of the passenger from the vehicle. If the vehicle tips over, this is an issue similar to when the vehicle is being rolling because of some lateral forces. But here the forces are just the one which act on the passenger themselves, and I want to know if the passenger will be ejected because of this maneuver or not. I hope I answered the question.
Okay, great. Thank you, Oren. I don't see any other questions, so why don't we continue on with the presentation?
Okay. Okay, so so what happened now is if we have any kind of combination, for example, this on the left you see right turn with acceleration. So if I'm looking at this rear passenger, there is one acceleration, that lateral acceleration, which will try to move him to the left here. And the other acceleration is because the vehicle is being accelerated and it wants to push the this passenger toward the back of the vehicle. If you look at this case, this is deceleration, which means I'm hitting the brakes and I'm making left turn at the same time. This force is because of the hitting. This is the acceleration because of hitting the brakes. And this is because the left turn. The front passenger and the right rear passenger experiencing the same thing. And the risk here is greater, and you see in the next. Okay, here is what happened. So here it is. I'm pushing my accelerator, the gas pedal as maximum, and therefore I have this acceleration we talk about is the 0.3 G. But at the same time, I'm making a sharp turn, so I have the lateral acceleration in this direction. These are two vectors, and therefore the total acceleration, what the person feels, is acceleration in this direction, which is about 0.6 G. Now, don't forget, in this particular direction, there is no restraint whatsoever. The hip restraint is sitting here. There is some restraint here, which I'll show you in a minute. So he has nothing to keep him in the car, unless obviously he's using the seat belt. If you look at the other case here, it's just similar. It's just turning on in the other direction. Now, if you look at stopping, so if I just stop, it means that this passenger moves forward or try to move for the acceleration of about 0.5 g. Depends on the coefficient of friction. But if at the same time, for example, I'm driving full speed at the road and I'm taking a turn, but suddenly I see something and I have to hit the brakes. So I have the brakes, this is the brakes, and this is the lateral acceleration. And now the total acceleration acting on the front passenger is about 0.7 g, which is 70% of his weight. You know, a person who is 200 pounds, there is a force acting on him, which is 140 pounds. If you want to imagine this, think about, here is the person, and I'm going to tie a rope around him, and I'm going to pull this rope with a force of 140 pounds. So there's a very large force which might cause him eventually to be ejected.
Or just very briefly, before we get off of those slides with the diagrams, a follow-up question from Christopher, who asks, with regard to rear passengers in a golf cart, with the height of the golf cart being lifted, does that add lateral force to create a higher risk of ejection of the rear passenger?
No. No, as I said before, the ejection is based on forces, accelerations, which act on the passenger. It doesn't matter if the golf cart is 2 or 3 feet above ground or 50 feet. As long as the golf cart is not tipping over, it doesn't make any difference.
Okay, great. Yeah.
I hope I answered the question.
No, great. I was just going to say, why don't we continue on with the program? That was great. Thank you, Oren.
Okay, so if I'm looking at a person sitting on the back of a golf cart, this is the back support and this is the seat. There are a variety of forces. First of all, there is a weight. This is the lateral force because of the lateral accelerations that we talk about. This is a forward or eventually backward force because of, let's say, acceleration forward. There's a normal force here, which is the reaction from the seat to his body. If he wants to move in this direction, there's the friction forces between him and the seat. And if there is a contact between the passenger and the hip restraint, there is a force acting right here. This is a full diagram of all the forces acting on the person, and we have to consider all of them in order to figure out he's going to be stable or not stable, ejected or not ejected. Okay, so when it comes to accident reconstruction, you have to ask your expert. He probably knows. Eventually, to follow the following these steps. He has to perform some experiments using the incident golf car or exemplar, because otherwise he will have hard time to do any kind of measurements of acceleration, etc. So he has to figure out the maximum speed of the vehicle, the acceleration acting on the occupants, and he has to use accelerometers in the right place and also in the right location. He has to mount these accelerometers at the center of gravity of the occupant. You have to figure out where's the occupant here, where is the center of gravity, and to put the accelerometers right there. Otherwise, he might get wrong results. Now, you have to construct a three-dimensional model of the golf cart for the simulation. You want to construct a model for the occupant, and I'll talk about this for a second. Once you have all the measurements that you made, you apply these accelerations to this simulation package, which calls ATB, and from there, you'll be able to determine either or not ejection will occur. I just want to make a little comment here. ATB is a program stands for Articulated Total Body, and it simulates the motion of a human body as being exposed to a known accelerations. And that's why we have to make the measurements first. This program is being used the last probably 25 years. It was developed by the car industry to see what happened in accidents. It was used in the Air Force to determine what kind of accelerations a pilot experiences while he's landing on, let's say, an aircraft carrier because of the high-speed approach. There are many applications for this. We use it to see what's the motion of occupant within a vehicle while during the accident, what surfaces has been hit, and what are the reaction forces. You can figure out the force between the knee and the dashboard, and a lot of information. So this particular program we used to analyze some of the results that we collected here. So these are the experiments that we ran. We ran
Oren, excuse me, just real fast, about that last slide. Can you go over again what GEBOD means?
GEBOD. This GEBOD is a program which is being fed by the height of the person, by the weight of the person, and by his gender, and it generates a model of a human, as you'll see this in a few seconds. Because we need to have this model, we put the model in the model of the vehicle in order to see what's the motion of the body in the vehicle. And I have a good example for this in a minute. In any case, the experiments that we run, we used a golf cart, and we run it at available speed in different radiuses here, starting with this about probably 5 feet, etc., and we increase this according to the steering wheel position. So you can see as the steering is only 90 degrees, obviously the radius of curvature is larger. It's about let's say 8 is about 24, 25 about 25 feet. Okay. Then you always have to measure what is the speed of the vehicle by taking two measurements of time. You make sure that you take this while the vehicle finishes the acceleration stage. So from here to here, the vehicle is really running at a constant speed. And this is just an example from our testing. And what you see here is in the blue, you see the acceleration as I am accelerating along a straight line. and you can see that we can reach acceleration up to about 0.3 g, and then we are reaching a steady state. I mean, constant speed. There's no acceleration anymore. The lateral acceleration, which is the red, is minute, so because we are moving in a straight line. And this is a similar thing. What you see here, this is my acceleration, and then I'm moving in a constant speed, and then I'm hitting the brakes as hard as I can. So acceleration forward is about 0.3 g, and when I'm hitting the brakes, the deceleration is about 0.5 g. That's the number that you saw before. And at this slide, you see a combination of forward acceleration and lateral acceleration as I'm driving along a circle. So this is the acceleration of the vehicle tangent to the circle. Therefore, I'm reaching some kind of a steady state here. As my velocity increases, the lateral acceleration increases. If you remember the equation, it says v squared divided by r. V, my velocity increases, and therefore the lateral acceleration increases too. And this is very similar, just a different steering angle. So as we make the steering sharper and sharper, the lateral acceleration will increase, but the tangential acceleration is just the same. This is how the speed of the vehicle increases. Okay, so that's one or two more examples. Okay, the model of the vehicle. This is the model of the vehicle. This is the front. We are not interested in the rest of the vehicle. It doesn't make any difference for us. This is the seat. This is the backrest. This is the tires. This is some kind of a little support to help people to step up to this platform and sit. By no means this is used as any kind of a safety feature. And this is the human model that I was talking about a second ago. This is called GE BOD, and it has all these parts, starting with the arms and the necks and the head, etc. What's really important about this, I have to make sure that we understand this is not animation like, let's say, Mickey Mouse of Disney. Mickey Mouse can jump, 100 feet and run 100 miles per hour, etc. This is, each of these members here have inertia, has weights, and each of these joints has properties, and the simulation is eventually solving the differential equation, the motion, the dynamic equation which describes the motion of each of these members. So obviously there are some limitations, but once we finish the simulation, getting all the results, then we do animation, which looks like Mickey Mouse kind of cartoon, but the results are physical. They're not imaginary. It comes directly from the solution of all these differential equations there. So here is an example. And
before we get into the examples, can I just ask you two questions?
Yes, I'll go back here.
A question from Brian, which goes back a couple of slides, I think. Why are three-dimensional models necessary when putting together an accident reconstruction? Well,
if you look at the model of the human here, the motion of the human is very complex, and you want to see what are the surfaces that are being engaged. For example, think about a vehicle who is being hit on the side. The head of a person can hit the B post. You might hit the knee might hit the dashboard. The arm might, who knows what. I mean, the motion is very, very complex, and therefore you want to have a three-dimensional model with all the physical properties in order to get a very good understanding what the motion of the person in the vehicle. This is one thing. Second is once any of these member engages with any of the surfaces or in the vehicle, we can get a good estimate what is the reaction forces between this surface and this particular member. So if we find out that, let's say, the arm was hit by the edge of the window, and we found out that the force is about 400 pounds, this information can go to an MD who would determine, yes, this is the reason why this person broke his bone. So we can relate the injuries to the impacts at different location on the body. So that's why we need a 3D simulation.
Okay, going back to the graphs that you showed a couple slides before the occupant model. Christopher has a question that asks, is the degree listed at the top the degree of the turning of the wheel or the turning direction of the vehicle?
No, the 360 is turning of the steering wheel. If you remember, let me bring it back for a second. You see, the only thing we could control is the steering wheel turning. So I turned the steering wheel for 90 degrees, and this resulted in a turning radius. The radius where the vehicle was traveling along of 8.36 meters. If you turn the steering wheel 180 degrees, which is like half of a revolution, obviously the radius, the turning radius becomes to be smaller. The best, the maximum you can do is to turn the steering wheel like 1.5 turns, and in this case you are almost turning on a spot, which is a very, very, very short, very, very small turning radius of the vehicle. So when you see this number here, 270, it means that I turned the steering wheel 270 degrees, and as a result, I go back to here, 270 degrees, it means that the radius that I was traveling along is about 5 meters, which is about 16 feet.
Okay, great. We have one more question from Elizabeth, who asks, if one is conducting accident reconstruction with exemplar as opposed to computerized simulation, is a dummy which is close to the ejected individual's height and weight going to be similar to accurately recreate the accident?
He has to use the exemplar vehicle to figure out what's the capabilities of this vehicle, to find out what are the speeds and what kind of accelerations. Once he found these accelerations, these are the accelerations he's going to use in the simulation. So at least we know that we are not, very far away from the performance of the vehicle. Now, when it comes to the person himself, we realize that people are different from each other, but this model is probably 95% percentile or something like this, and it's being used for years. and it was accepted in court without any problems.
Okay, great. Why don't we continue on with the examples?
Okay, so let me go here. Okay, so this is this is an example, which means I'm running along a circle about 27 feet in radius with relatively small speed, very low speed, and these are like snapshots along the trajectory, and you can see that there is some effect. At least you can see this on the head. You can see the hand is moving a little bit. From here it comes out, etc. But the person is not being ejected. As I'm increasing the speed, what will happen is that eventually it reaches the point that the person is being ejected, and it moves along this line. If you watch this particular photo, you can see that he falls on his head eventually. It's difficult to see. Usually we are generating a movie or a little clip that shows all the motions, but here I just took every half a second or so a snapshot to see what happened. If we're just moving forward with very high acceleration, the vehicle is moving in this direction. I'm sitting like this, and suddenly you can see as the acceleration, as the vehicle moves to the left, eventually the person is being ejected outside. This little restraint that you see here is not helping whatsoever. This is another simulation. The difference is we took 12 years old child because of one reason only, and the reason is that his feet is not touching this little platform that you have here. In the other cases that you saw, we used adult, and therefore his feet was touching this surface and eventually help him a little bit with the friction here to stabilize himself. In this case, the kid is not touching the surface, and therefore he is by far less stable than the adult. And in this particular snapshot, you can see what I was saying maybe at the beginning, that a lot of the injuries is head and neck injuries because the person is tipping over this hip support. If he tips over, this is like a pivot point, and therefore his head is moving down. These are the results that we had. Only at very large radius, there was no ejection. Obviously, in the other radiuses, we ran relatively fast, so there was ejection, which just tell you this is a dangerous situation. This is what we were looking at is what the ejection of the person from the back. And the reason we did this, because there are some publications and some other information that some work that people did on the ejection of people from the front. So we wanted to tackle the question, what happened in the back, because looking around here at the university, most of the golf carts that we have a back seat, and there is always somebody there. And I myself was involved with one or two cases of accidents, and that's the results that I'm showing here. What we have to do, we have to do a few things. This is a typical back seat. This is a very low hip restraint. These bars here just help you to step up to this platform. The minimum you can do is eventually to increase the height of the hip restraint, because it's very easy to tip over here because most of your body mass is here. But if this is higher, it will be by far less. It won't be so easy to tip over. Second possibility is just to change the whole thing. This is just one of the ideas that we came with. So you have restraints while you are moving. If in case you're falling backward here, and you have high restraints when you are, in case you are ejecting to the left, and obviously you have this opening, to get in and out of the car. So my recommendation, I don't know who is going to listen, is my first recommendation is not to allow low-speed vehicle on city streets, because their crash resistance is inferior to the smallest passenger car. There's no question about it. So any accident might be quite severe. The second thing is to require some kind of licensing or some kind of minimum training, which will make the driver aware of the risk in this particular vehicle. In most vehicles, they have these labels, don't do this, don't do this. But you guys know just the same. I know that eventually nobody reads the labels, and they just go in and drive. Then you have to require seat belts not only on the back but also in the front, and to enforce it. Otherwise, people don't use it. And the last thing is, since people don't really use seat belts, you want to make sure that the passive restraints, like the hip restraints or some others, will be by far more efficient. The other issue that since we are talking about it, they have to improve the quality of the ignition. Okay, if you see the keys being used to start these cars, you can see you can use a screwdriver and turn this on. And I'm aware of one or two accidents where a little kid was playing around with this keyhole, and suddenly the vehicle started to move, and it was not a very pleasant situation. I think this was the end of my presentation. We have 5 minutes. I'll be glad to answer any questions.
Okay, great. Thank you so much, Oren. I think there are a lot of takeaways for all of the attendees. It shows that you put a lot of time and effort into the presentation, and we thank you for that. Going back to the slide where you posted your experiment results, Christopher has a question, and he asks, is this slide based on radial feet of the turn or the length of the cart traveled before ejection?
No, this is we are running the vehicle at maximum speed, and we maneuvering it along a certain radius. So we are running about 12 miles per hour at a radius along a circle, which has a radius of about 5.3 feet. If this is the case, not you personally, but the passenger can be ejected. We're running at 12 miles per hour at a radius of about 10 feet. They are being ejected. They are running at 12 miles per hour at 25 feet radius, and we are not ejected. And the reason for this, I just want to remind you, the acceleration is the velocity squared divided by r. So velocity squared, since we are running the same velocity squared is constant. If the radius is small, the result is large. If the radius is large, the result of v squared divided by r is smaller, and therefore smaller acceleration are being exerted on the passenger.
Okay, excellent. Thank you, Oren. Moving a couple of slides ahead to where you inserted the bars as a proposal or as kind of a thought experiment. Kimberly has a question, and she asks, is the shorter of those two bars the same height as the bar on the right-hand side of the front seat of the golf cart passenger seat? So on the passenger seat. Yes, I believe she's referring to those slides. So is the of the two bars the same height as the bar on the right-hand side of the front seat of the golf cart?
Well, not necessarily, and the reason is that sometimes the whole back seat is aftermarket. So you can buy the back seat from, maybe 10 to 15 different manufacturers, and it will fit a regular a golf cart, but each of them will have a different kind of heat restraint, and therefore there's a good chance it will be different from the one that came with the golf cart itself.
Okay, that's good to know. We have a question here from Elizabeth who asks, what's your thought on handholds as hip restraints? Where do you think handholds should be placed and why?
Well, let me go one forward. Eventually, what you see right now on the screen is some kind of handhold. And what's nice about handhold that it provides you very high stability. You can apply forces. You can hold yourself. You can resist any maneuvering. It's by far better than the passive hip replacement. This is one thing. Second, if you have hip replacement, I'm sure all of you are sitting on some kind of office chair, and if you have armrest, look at the armrest as a hip restraint and hold it with your hand and see how much resistance you can provide of moving of your body left and right. It's very little. We don't have these capabilities. You cannot exert very, very high forces when you are holding the hip restraint. You can apply very large forces if you are holding, let's say, right here and right here. Very little force if you are holding here.
Okay, great. And this will be the last question, Oren. In your experience in these accidents, what's the major cause? Is it people driving too quickly, making too sharp of turn? What's the major cause that you see in most of the accidents that come across your desk?
Most of the time, they do maneuvers too fast. They don't realize it, but if they're driving, 17 miles per hour, and they take very sharp turn, this cause very high accelerations. But there is another issue, which is we have to realize, which is human behavior. What I'm trying to say is most of these vehicles are being operated in environments which people are familiar with. It's not that, when I'm driving from here to Orlando, I don't know what the road looks like, so I immediately pay by far more attention. But if I have to drive in my neighborhood and I know every road and every little turn, I don't put so much attention. And as a result, I might find myself a little bit of surprise because, I know where it is, but here it is and it's too late. So this is another factor that I saw at least once or twice, that people are driving in a place that they do know that is a sharp turn, but still they don't they don't conceive that here comes a threat. And obviously,
Okay,
and on the golf cart, you're on a mood of vacation in any case. So you don't have this feeling. Listen, I have to worry about it. No, I'm playing. Everything is okay. I'm on vacation, and this caused also some problems.
Right. Well, thank you so much, Oren, for the time and the effort that you put into the presentation. Are there any concluding remarks that you'd like to make?
Well, if you are playing golf, be very careful, in particular when you go downhill, and if you are trying to turn as you go downhill. If you have one in your neighborhood, make sure that your kids are not driving it, and when you drive it, don't go full speed.
Okay, just to wrap things up here very quickly, if you'd like to speak to Oren about a specific matter that you're working on, please give us a call here at TASA. Our telephone number is 800-523-2319. As I stated during the introduction, tomorrow morning I'll send out a link to the archived recording of this program. Included in that email message will be a copy of the PowerPoint presentation that Oren used during today's program. The archived recording of this program, as well as all of our previous programs, can be found in the TASA Knowledge Center. If you visit our website, www.tasanet.com, and go to the bottom of the screen, you'll see a box that says TASA Webinars. Click on that box and you'll be taken to a full list of our previous programs. Our next webinar for legal professionals, Human Factors in Product Liability Cases, will take place in 1 week, next Tuesday, May 14th at 2 p.m. Eastern Time. I'll include a link to register for that program in the follow-up email that I send out tomorrow morning. If you have any follow-up questions or comments, please feel free to email me at any time. My email address is mhyde@tasanet.com. We do take all of your comments under consideration, and they help us to produce better programs. With that, I'm going to end today's program, and I hope to see you at future TASA events.